Hello guys, this lecture is the review on vectors part 2. Outlines of this lecture are the scalar triple products of the vectors and dot products of the vectors and their applications, then physical interpretation of the scalar triple product and reciprocal set of the vectors. So first of all we will discuss the scalar triple product of three vectors A, B and C. So you can say A1 is A1 I cap plus A2 J cap plus A3 K cap. Okay. B is equal to B1 I cap plus B2 J cap plus B3 K cap. C is equal to C1 I cap plus C2 J cap plus C3 K cap. Okay. So scalar triple product. So if we consider the literal meaning of this scalar triple product, triple means there are three vectors, product of three vectors, triple product. Scalar means the quantity which is obtained after the scalar triple product is the scalar. So scalar triple product of three vectors can be written as A dot B cross C. So the second vector is the cross product of the two vectors, and then the dot product of A and then B cross C. So the another notations for this scalar triple product are A, B, C inside a big bracket, and some properties of scalar triple products are we can write B dot C cross A is equal to C dot A cross B. This is equal to A dot B cross C. Okay. So if you look this property, we can say that if we put vector A, B and C in a cyclic manner and we preserve this cyclic ordering, then the scalar triple products of A, B, C will remain same. Okay, means A dot B cross C, and then we start with B dot C cross A and then C dot A cross B. So these are equal. So the question, the one question you can raise, why these three are equal? So we will discuss in the next page. Uh, the scalar triple product of the three vectors can be calculated by taking the dot product of these two vectors. One vector is A and another vector is B cross C. So the cross product of these two vectors can be written as a determinant of order 3. The first row of which is ijk, second row is b1, b2, b3, and then third row is c1, c2, c3. Okay, taking the dot product of a means a1 I cap plus a2 j cap plus a3 k cap. Okay, So taking the dot product of these two vectors, so we can write this as a determinant of order 3, the first row of which is a1, a2, a3, and second row is b1, b2, b3, and then c1, c2, c3. So applying the properties of the uh, determinant, expansion of the determinant. If we interchange the first and second row, so the minus 1 sign will be there. The first row will become b1, b2, b3. Second row will be a1, a2, a3, and c1, c2, c3. Again interchanging these two, second and third row. So we can get again a minus sign. So then minus minus will become the plus. So you can write b1, b2, b3, c1, c2, c3, and then a1, a2, a3. So as we have written this a dot b cross c in the form of this this determinant. The first row of this determinant is the first matrix, first vector. Second row is taken from the this second vector, third by this third vector. So this can be written as b dot c cross a using same concept. So we can say that a dot b cross c is equal to b dot c cross a. Fine. And similarly we can write or we can prove that this is equal to c dot a cross b. So we have finished the proof of this portion. So next we will discuss the physical interpretation of the scalar triple product. Okay. So we will discuss now the physical interpretation of scalar 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 triple product. So first we will say that we can say that what is the scalar triple product of physically what represents the scalar triple product. So consider the vector a, b, and c along the three coterminous edges of a rectangular parallelopipe. You can say parallelopipe, not rectangular parallelopipe. So the physically the scalar triple product of A dot B cross C is the volume of the of the parallelopipe. We can say that this is A, this is B, this is C, this is O dash. Okay, so O, A, you can say this is B, this is E, so E dash. You can say OA, OA, E dash, E, O dash, C, A. Okay. So the volume of this parallelopipe, we have to prove this. So how we can prove? First, we will consider this portion, this portion. So B cross C is a vector which is perpendicular to the plane containing B and C, containing the vectors B and C. So parallelopipe is a solid body. Suppose the base of this solid body is OBO dash C. Okay. So the area of this parallelogram is modulus of B cross C. This is the area of parallelogram OBO dash C. And what is the height of this body? Because if it is a solid, so its volume is the area of the base and perpendicular uh, drawn from this top at the bottom. So we have to take the projection of this vector A over this base. Okay. So suppose uh, this vector is a eta cap. Eta cap is a unit vector which is perpendicular to the base containing the vectors B and C, and perpendicular to this, and suppose phi is the angle between the vector A and eta cap. So the component of this vector A along this will be A cos phi. Okay. So this is the height of that solid. So if you will multiply by this height to the modulus of B cross C, so you can write this is equal to vector A dot B cross C. Okay. So the volume of this parallelopipe is nothing but it is the scalar triple product of three vectors which are the coterminous edges of this parallelopipe. Fine. So suppose we have to prove that the 4 points are coplanars. So fix a point with another points. You can make the three vectors and check if the scalar triple product of these vectors, these three vectors, is 0. It means volume is 0. So the points will be coplanar. So to check the coplanarity of the 4 points, you can use this concept. So let us try one more example on this physical interpretation. So suppose we have to find the volume of a parallelepiped whose edges are represented by, say, the vector A is 2i minus 4j plus 5k. Vector B is, say, I minus j plus k. Vector C is 3i minus 5j plus 2k. So to check the volume of this parallelepiped, we must find the scalar triple product of three vectors A dot B cross C, and this is equal to the components of the first vectors are 2 minus 4 5. The components of the second vectors are 1, then minus 1, then plus 1. The components of the third vectors are 3 minus 5 and then 2. Okay, so let us try this one. So 2 into minus 2 plus 5, and then taking here minus sign, so minus minus plus, plus 4, so 1 into 2, 2 minus the product of 3 and 1, and then plus 5, which is multiplied by 1 into minus 5 minus 5, and then plus 3. So this will be 3 to the 6, minus 1 into 4 minus 4 minus 2 plus 8 minus 10. So it will be minus 8. Okay, so the negative sign here represents that angle phi which we have treated there. It is an obtuse angle, but we have to find the volume, so taking the absolute value of this, the volume of the parallelepiped is 8 unit. Sometimes we have to solve the problems like for example, suppose find the value of lambda if the volume of a parallelepiped whose edges are represented by A is equal to lambda I cap minus 4j plus 5k, and then B and C are similar as in the previous example. So find the lambda if the volume of this is 0 or these three vectors are coplanar. So if the volume of the parallelepiped is 0 or the vectors are coplanar, so you have to start with A dot B cross C is equal to 0, means you have to consider that this scalar triple product is 0 and then find the value of that unknown. Okay, So next we will discuss the vector triple product of the vector triple product. Means suppose we have the three vectors A, B and C. So their vector triple product can be written as A cross B cross C, and by convention its value is the dot product of the vector A to the C, not with the adjacent vector. So first you will take the dot product of A with a vector which is not adjacent to A, A dot C, and the remaining vector B is outside. Means the ordinary multiplication between the dot product and B, vector B is there, minus, and then take the dot product of A and B and ordinary multiplication of this value with the vector C. Okay. So suppose you have to find B cross C cross A. So this vector is outside. So then take the same rule we have to apply here. Take the dot product of this vector A, not with the adjacent vector. So A dot B, remaining vector C will take the ordinary multiplication with this one, minus the dot product of A with the remaining vector C, and other vector is B. So if you look this first relation and this second relation, you can say that A cross B cross C is equal to minus of B cross C cross A. Or you can explain this result with the help of the property of the cross product, because the cross product of two vectors is not commutative. Means if you take the two vectors P and Q, so P cross Q P cross Q is equal to minus Q cross P. Okay. You can also explain in this way. But according to the definition of the cross product of three vectors, you can explain this one. So before discussing the Gauss divergence theorem and differentiations, Green's-Stokes theorem, so these are the basic concepts for the multiple products of the vectors. So we can discuss some more examples based on the scalar triple product. So we will discuss some few more important examples. For example, prove that A plus B, B plus C and C plus A. We have these three vectors and we have to find the scalar triple product of these three vectors, and this is equal to 2 times of the scalar triple product of these three vectors. twice of this. So you have to prove this one. Prove that. So I think we should start with this left hand side. So if we have to find the scalar triple product of these three vectors, so we can take the cross product of uh, these two. So taking the cross product of these two, we will get B cross C plus C cross C plus C cross A plus B cross A. We will get the four vectors. This goes to 0 because the cross product of a vector to itself is 0. Then we will take the cross product, sorry, oh, undo. Taking the dot product of A plus B with this one. So taking the dot product of A with this BC, B cross C, so that can be written as ABC. If we will take the dot product of this A with the ACA, so that will be ACA. So the scalar triple product of three vectors will be 0 if two are same, because if these two are same, their components will be same, and in the determinant of this the two row will be same, so the value of the determinant will be 0. So this is the explanation why it is 0. A, the next dot product is A B A, so this is again 0 because the two vectors are same, plus not taking with the dot product with B, so BBC, this is again 0 plus we can take BCA, this one and this one, and then BBA, so this one 0 because the two vectors are similar, this is 0. The only non-zero values are this one and this one, and BCA can be written as ABC, maintaining the cyclic order. So 2 times of ABC will be the right hand side, so hence proved. Okay. So friends, we will consider the next example. uh, Prove that LMN means scalar triple product of these three vectors with the vectors A, B, C. This is equal to the determinant L dot A. The first row is L dot A, then L dot B, L dot C, then M dot A, M dot B, M dot C, then N dot A, N dot B, and N dot C. Okay. We have to prove this result. Since uh, L, M, N and ABC are the vectors, so to get the solution of this one, we can consider L as L1 I plus L2J plus L3K, and similarly we can write M is equal to M1I plus M2J plus M3K. Okay, and N is N1I plus N2J plus N3K. Similarly, we can write A is equal to A1I plus A2J plus A3K. Okay, and so on. So if you will take the dot product of L and A, L and B, and L and C, so the situation will be like that. Means first we will calculate the left hand side, okay, and then we will try to prove the right hand side. So the left hand side of this problem is scalar triple product of three vectors lmn multiplied by the scalar triple product of the three vectors ABC. So the first scalar triple product is a determinate. The first row is the components of L, means L1, L2, L3. Then second row is the components of M, M1, M2, M3. Third row is the components of the third vector N1, N2, and N3. Similarly, the second scalar triple product is also a determinate, first row of which is A1, A2, A3. Second row is B1, B2, B3. Third row is C1, C2, C3. So this is the product of two determinants. We have to prove this one. So look this part, L dot A, L dot B, L dot C. So the first row, we need the first row. The first row is required as the dot product of L with the three vectors A, B, and C. So this can be possible. This can be possible if we take the multiplication of the determinants by the row by row multiplication. Row by row multiplication. So the first row with first row means you will get L1 A1 plus L2 A2 plus L3 A3, means you will get L dot A, and then first row multiplication with second row, first row of the first determinant and second row of the second determinant, then it will be L dot B, and then the first row of the first determinant and third row of the second determinant, so L dot C. And similarly we can find the product of this second row and then the dot product with the first row, second row, and then third row. So we will get a m dot a, and then we will get m dot b, and then m dot c. Similarly, n dot a, n dot b, and then n dot c. Okay. Hence proof. So this is equal to the right hand. So next we will discuss the reciprocal set of the vectors. Suppose we have three non-zero vectors A, B, and C, which are non-coplanar. So if these are non-coplanar, so it means their scalar triple product is not equal to 0. So there exists a set of non-zero vectors A dash, B dash, and C dash. Okay. A dash can be written as B cross C upon a scalar triple product of ABC, and similarly B dash can be written as C cross A upon a scalar triple product of ABC, and similarly C dash can be written as A cross B and then scalar triple product of ABC. Okay. So why this set of vectors is called the reciprocal set of vectors? Why it is so? Because if you will take the A dot A dash, that will be 1, means their dot product is 1. So this makes the same sense if you take A into B is equal to 1 and A is non-zero. Suppose A and B are two real numbers, so B is equal to 1 upon A, means reciprocal. B is the reciprocal of A. So the same sense is here. The dot product of these two vectors is 1. Okay, these two pairs, and similarly we can prove that B dot B dash is 1 and then C dot C dash is 1. Okay, or you can prove it easily if you will take the dot product of A with A dash. So A dot B cross C will be in the numerator and ABC is also in the, so this will be cancelled and you will get the 1. But if you will take the dot product of a vector from a set of the reciprocal, from the set of reciprocal vectors, and you take the different vector from the basic set, means this one. For example, you take the dot product of A dash with B, so this will be 0. Similarly, if you take B dash with C, this will be 0. Okay. But if these notations are a and a dash, so then value will be 1. Okay, similarly if b and b dash, so value will be 1. So if these are not similar, these are different pairs, so the dot product will be 0, because in this case the numerator of the dot product will have the two similar vectors, and the scalar triple product of the three vectors, if two are same, will be 0. Okay, so we should stop here. अगर आपको ये चैनल पसंद, ये लेक्चर पसंद आया है तो आप इसको सब्सक्राइब करें, एंड यू कैन हिट ऑन द लाइक बटन. थैंक यू.